isotopes and radioactivity. I've used the word isotope, and going back to hydrogen, the simplest element, hydrogen has 3 isotopes. Isotopes are different varieties, if you like, of the same atom. In other words, all the isotopes of an atom have the same number of protons in the nucleus, but they can have differing numbers of neutrons, so they have differing atomic weights, and this gives them differing properties. We've already seen that the 235 isotope of uranium is fissile, the 238 isotope is not. Hydrogen, the simplest atom, has 3 isotopes. There is ordinary hydrogen, which I've described with 1 proton and 1 electron. There's a second isotope called deuterium. This occurs naturally. In any bucket of water will be a small amount of deuterium oxide. Deuterium contains a nucleus with 1 proton and 1 neutron, so it's twice as heavy as ordinary hydrogen. It has 1 electron in orbit. The third isotope is called tritium. 1 proton in the nucleus, 1 electron in orbit, but 2 neutrons in the nucleus. So it's 3 times as heavy as ordinary hydrogen. But it is chemically, it is hydrogen. Physically, of course, it's heavier. This is the origin of the term heavy water, because in any ordinary sample of tap water, most of it will be H2O, a little bit will be D2O, and I'm talking parts per million here, and an even smaller proportion will be tritium oxide. If you enrich the proportion of deuterium oxide and tritium oxide, you produce heavy water. A bucket full of heavy water, all tritium and deuterium oxide, will be heavier in weight than a bucket of ordinary water, because the nuclei of the hydrogen atoms in the molecules are twice and 3 times as heavy as ordinary hydrogen. Now, once the phenomenon of radioactivity had been discovered, physicists began to study the nature of radioactivity, and 2 notable physicists made a study of this, namely Ernest Rutherford, Lord Rutherford, who finished up at Cambridge University, and Frederick Soddy, who was a chemist, I think, from Oxford. And they studied the radioactive decay of an element, and they discovered that the elements decayed according to a mathematical law, in that they had a certain half-life. The meaning of the half-life is, for example, if the half-life is a year, it means that if you have a kilogram of an isotope, inside 1 year, half of that kilogram will have decomposed into other products. Half will be still remaining. In the second year, half of that half will decay. So at the end of the second year, you'll have a quarter left. In the third year, half of that quarter will decay. So at the end of the third year, you will have an eighth left. At the end of the fourth year, half of that will decay. You'll have a 16th, and so on. So you follow a decay law where it can take quite a long time before the thing decays completely, which, as I indicated earlier, it's taken many millions of years for uranium isotopes to decay to form lead. So this concept of half-life becomes very significant once we start talking about nuclear safety. If we produce radioactive isotopes as part of our power generation processes, the half-life of the products will present us possibly with a storage problem, or not, depending on the value of the half-life. Physicists have made elements very much heavier than uranium by cramming more and more protons into the nuclei. The problem, they've gone up to element number 100 and nearly 120 now. Many of these heavier elements are very unstable. For the reason I already said, namely too many protons crammed into the nucleus. So the half-life of an isotope can vary between tens or even thousands of years, down to an hour, a minute, a second, a millisecond, a microsecond, a nanosecond, and even quicker than that. If the half-life of a highly radioactive isotope is measured in microseconds, then this will not create a problem, because as soon as you generate some, most of it will have decayed within a second. If, on the other hand, the half-life is 1,000 years, then you may have to look after that stuff for 4,000 or 5,000 years before enough of it's decayed to make it safe. So that's the concept of the half-life. It's the concept of the isotope. An isotopes are variations of elements where you've got chemically the same element because you've got the same number of protons in the nucleus, but differing atomic weights due to a differing number of neutrons in the nucleus. And this is an important concept that we need to draw on once we start talking about radioactive waste and waste disposal, because these issues become very important then. Radiation is invisible. People need to be protected from excess exposure to radiation.